So the first talk we have is the second of our best paper talks. Hello, you're quiet.
Hi, are you able to hear me?
I'm just waiting for quiet in the room.
Okay.
Okay, yeah, so we have the second of our best paper talks now. This is by Nadia Henninger and Keegan Ryan on the hidden number problem with small unknown multipliers, cryptanalyzing mega in 6 queries and other applications. And Keegan will give the talk virtually.
Great, thank you for the introduction. Can I get confirmation that you can hear me all right?
See you.
All good in Zoom.
All right, perfect, thank you. All right, so yes, I'm Keegan Ryan, and I'm presenting the hidden number problem with small unknown multipliers, cryptanalyzing mega in 6 queries and other applications. So to begin this talk, I'll mention a little bit about what Mega is. So Mega is an encrypted cloud storage company. So they're cloud storage, so that means you can upload files to their service under your account. But the fact that they're encrypted is because that they care about user privacy. So even they themselves should not be able to see the plain text of the files that you upload. But these privacy guarantees were shown to be false in this paper from this year, Malleable Encryption Goes Awry from Beckendahl, Haller, and Patterson, where they showed that this assumption was false and it was possible to recover secret material from the service. Mega released the security update in a blog post discussing these attacks. And in this blog post, they noted that these vulnerabilities affected users who logged into their account at least 512 times. So these vulnerabilities were not thought to affect people who only logged into their account a few times, which was the vast majority of users. It only affected automated systems. So our work was showing that these attacks were in fact possible with much fewer login attempts, in fact, only 6 login attempts. And there's even newer work than that that shows it's possible to do it in 2 login attempts, and I'll talk about that at the end. So because all of these attacks rely on a number of login attempts, it helps to go through what the login process is for Mega. And recall that because Mega is an encrypted system, we need to make sure that the client has the encryption keys that they need and that the server cannot see the plaintext data. And one of the problems with encrypted cloud storage systems is the problem of logging in on a new system where you don't have all the same key material stored. In fact, the only secret material that the client has when logging in from a new system is their password, or maybe an AES key derived from their password. And they have to somehow use this to bootstrap the remainder of the key material that they need to decrypt their files. So the server can't store the key material directly. So instead, the server stores an encrypted form of this key material. During the login process, the server sends the client's encrypted private key material. And then the client can use their password-derived key to decrypt it. Once the client decrypts it, then the server and the client do this RSA type challenge to verify that the client successfully decrypted the challenge and decrypted the private key. So the server creates a challenge plaintext for RSA, sends it to the client, the ciphertext, and then the client uses the decrypted private key to decrypt the RSA ciphertext, takes the plaintext, and then sends that back to the server as a way of confirming that the client was able to decrypt the challenge. The server then authenticates the client if the challenge value matches what's expected. And then the server can go on to send the client the encrypted files. So in reality, the client doesn't send the full plaintext buffer. The client only sends 43 bytes of the buffer for verification. Now, this is how things are supposed to work normally, but as part of the threat model, we need to assume that the server could be acting maliciously in trying to recover the client's sensitive files. So in this case, we're considering an attacker who is impersonating the server and has access to everything on the server. So you'll notice here that I've written that this is AES in ECB mode, which is the first of 2 cryptographic weaknesses that we'll discuss in this system. So this is weak because in AES ECB mode, it's possible for the attacker to modify different bits and different blocks of this encrypted private key, and then those corresponding blocks will be modified in the corresponding plain text. So the attacker can modify different 128-bit blocks in this encrypted form, send it to the client, and then when the client decrypts it with their password-based key, then their corresponding private key will have 128-bit blocks be modified. So some of the private key values will be the same and some will be different. Then during this RSA challenge, when the client tries to decrypt the challenge ciphertext, it's going to try to decrypt it using some private key values that are correct and some private key values that are incorrect. So this decrypted ciphertext now has a little bit of information about both the private key and the modification, so the private key mixed into it. When the client sends the resulting message to the attacker, it does not check that the 43 bytes were properly padded with this weird custom padding scheme. Instead, it just extracts 43 bytes from the most given bytes of that buffer and sends it directly to the attacker. So then the goal for the attacker here is to use these 43 bytes to somehow infer information about what was on the client side, the information about what were the unmodified values of the private key and what were the modified values of the private key. So this brings us to the attack of Beckendahl, Haller, and Patterson for their original attack on Mega. And this is just one of several attacks that they present in their paper. So this is a key recovery attack. And in this attack, the private key is represented by 4 values, Q, P, D, and U. And then they use this ability to modify AES ECB ciphertext to change the value of U, which is the RSA CRT coefficient. Because of this, the 43 bytes fall into one of 2 cases, which allows them to do a binary search on the value of Q. So every login attempt and every 43 bytes from the client, they narrow down the value of Q by 1 more bit. This means that after 512 login attempts, they have 512 bits of information about Q, which means they can use coppersmith's method to efficiently factor the rest of the modulus and recover the key. But this seems a little excessive. 512 login attempts, where each one has 43 bytes of data in it, but for every 43 bytes of data, you only get 1 bit of information. So it seems like we should be able to do a lot better and be a lot more efficient. And to get this efficiency, we need to consider exactly where these 43 bytes come from. So Mega clients used Garner's formula to compute the decryption, and then it took the most significant bytes from this, this value as the 43 bytes that it sent to the server. Now, Garner's formula is complicated here, so we can simplify it a bit. There are several values that do not change, so we'll just replace them with X. There's this value M sub Q, which because of Garner's formula is small. And we can combine the uncertainty in the value of M sub Q with the uncertainty in the least significant bytes into a single value, which we have as the error term E. And then we'll also note that this multiplier U is based on those modified 128-bit AES blocks. And the modified value is only 128 bits. So if we can learn what this unknown 128-bit value is, then we can see what the result of an AES decryption is. We've created an AES decryption oracle, and then this allows us to decrypt the rest of the key. So our goal here is to recover this multiplier. And we can say this a little bit more generally, which we do here. And this is actually the hidden number problem with small unknown multipliers. So this is the main problem of our talk. So I'll focus on it just a little bit more. We have this problem where we have a number of samples that are a product T times X plus E. And our goal is to recover the values of T. One of the issues with solving this problem is that there are 2 unknowns for every new sample and 3 unknowns in that entire equation. So the more samples that we have, the more unknowns that we have to solve. You may also notice that this resembles the hidden number problem from Bonet and Venkatasan in 1996, except in this case, the multipliers are unknown, so we can't use the multipliers to perform the same sort of lattice attack as was used for the hidden number problem. Another challenge in solving H&P sum is we can't do linearization because this value of Ti times X mod n is not bounded mod n. So we can't introduce a new variable here and use a bound on that to solve for the value. So there are many challenges to solving H and P sum, but if we can solve them, it'll allow us to cryptanalyze mega with only 6 samples. So it would be good if we can overcome these challenges. And in fact, that's what we do in the paper. We find a way to solve this problem. And a way to see how to solve this problem is by starting with 2 samples. If we start with 2 samples, A1 and A2, it's easy to see that a linear combination of these samples can be used to cancel out X. And after we do this linear combination, we see that the value of this linear combination is small, the coefficients are small, and this is a linear combination of known values. So if we can recover the coefficients, we've recovered the multipliers, and we've solved the problem. Now, you may see a small linear combination of known values with small coefficients and think this sounds like some sort of lattice problem. And in fact, it absolutely is. We can set up this dimension 3 lattice with these known values. And because of the equations on the previous slide, we know that this lattice contains the short vector given here. So if we use lattice reduction to reduce this lattice basis, then it will find this short target vector. And we can come up with bounds that show exactly for what values we can find this short target vector. Now, this works for solving H and P sum with 2 samples. And we can ask, how do we do it with 3 samples? How do we do it with more samples than that? And there's a very obvious way to generalize this lattice construction for 3 samples, and we do so here. So instead of a dimension 3 lattice, we have a dimension 4 lattice. And instead of having that one target vector for the 2 multipliers, we have 3 different target vectors for each of the 3 different pairs of values. Now, for each of these target vectors, you'll notice that we only consider a pair of multipliers at a time, and all of the other values besides that are 0. So if we can reduce this lattice to find any one of these short vectors, then this will give us information about 2 of the multipliers. And if we repeat that enough times, we'll get information about all of the multipliers. So we have this lattice construction. Let's try applying lattice reduction. And unfortunately, none of these target vectors, these short vectors in the lattice, are found by lattice reduction. So what exactly is going on? Well, we have this example here where we have an instance of H and P sum with these 3 multipliers. And after lattice reduction, we see that lattice reduction does find short vectors, but it doesn't find the short target vectors that we're looking for. H and P sum, this lattice reduction for H and P sum finds a dense sublattice spanned by these first 2 short vectors. And although neither of these are the target vector, we can show that the target vectors lie in this dense sublattice. So we want to find target vectors that do have these zeros in the correct spots. So one way of doing this is by taking the basis for this dense sublattice and calculating the Hermite normal form. And after doing this, the Hermite normal form finds vectors with zeros in the correct places. And this allows us to find the target vectors, which allows us to recover the multipliers. In this case, 264 and 185. And even though this gives us just 2 of the multipliers, we can always shuffle around the samples and reorder them, run this process again, and get 2 other multipliers. So we're able to solve the hidden number problem with small unknown multipliers by using this lattice construction and by doing a combination of lattice reduction and calculating the Hermite normal form. And fortunately, this extends well and generalizes well for even more samples in higher dimension. We make a couple observations for why this strategy works. And one of the interesting things about this attack is that we're able to work around the challenges involving X by canceling it out. And we don't cancel it out explicitly, we cancel it out implicitly with the construction of our lattice. So this allows us to work around the limitations for the linearization problems that we were running into earlier. Another observation that we have here is that we're using lattice reduction not to find a short vector, but to find a dense sublattice. And although there are other examples in the literature of using lattice reduction in this way, it definitely is a more unusual way of using lattice reduction to solve a problem. So we have a way to solve the hidden number problem with small unknown multipliers. And we're looking for ways to apply this problem in other situations. And one such situation that came up was the RSA implicit factoring problem. Now, the RSA implicit factoring problem has nothing to do with Mega, but it does involve RSA moduli, and it's particular RSA moduli with unbalanced factors. And then the larger of the two prime factors shares bits with the factor from the other samples. So the goal of this problem is, given the moduli, recover all of the factorization. Now, we can consider this with the most significant bits shared, as is shown here, but there's also a version of the implicit factoring problem where the least significant bits are shared, where a combination of the most and the least significant bits are shared, or where the middle bits are shared. And we can consider all of these cases. And fortunately, this does seem to resemble the hidden number problem with small unknown multipliers. In particular, we have a number of known samples given by the moduli. The shared value x that's shared between all samples is just the shared most significant bits. Our small unknown multiplier is just this smaller of the two prime factors q sub I. And then the error term just comes from the fact that the RSA moduli are unbalanced. So this gives us the reduction for the case where the most significant bits are shared, but there are also reductions for the other cases that we have. Now, we can compare the performance of this reduction from the implicit factoring problem to HNP sum, and we can compare how our lattice-based approach for solving HNP sum performs when using it to solve the implicit factoring problem. And we'll acknowledge that there are Coppersmith-based methods for solving the implicit factoring problem, but those aren't the ones that we're comparing to here. So in the case where the least significant bits are shared, we do improve upon the results of May and Ritzenhofen from PKC 2009 that originally proposed this implicit factoring problem. In the case where the most significant bits are shared, we are pretty close to the performance of the work of Fougère, Marinier, and Renaud from PKC 2010, although we are slightly worse. In the case where the middle bits are shared, our lattices are polynomially smaller than the lattices in that same work. So if there are k samples, then our lattice has dimension O of k rather than O of k squared, which is particularly important when you have more than just a few samples. And finally, in the case where both least significant and most significant bits are shared, there is no direct lattice construction in the literature for us to compare to. So our reduction is especially good there. All right, so we've gone through the design of Mega. We've talked about how to solve the hidden number problem with small unknown multipliers, and we've shown this reduction for the implicit factoring problem. But why does all this matter? So the original attack of Beckendahl, Haller, and Patterson, where they showed that 512 logins were enough to attack the security guarantees of Mega, came out on June 21st, 2022. And at that time, Mega acknowledged the impact for users who had logged in more than this many times. Then in July of 2022, we disclosed the 6th login attack, which caused Mega to update their blog post to say that this attack actually affected the vast majority of users. And then it doesn't even stop there. In September of 2022, Albrecht, Haller, Markova, and Patterson showed that there is a 2 login attack on unpatched systems, and they also showed that there were additional attacks on the patches that came out for the original set of attacks. So the attacks are clearly getting better over time, and we can wonder about how much better they will get beyond there. I don't think they'll get much better, but feel free to talk to me later about that. But none of this would be possible without the original work of Beckendahl, Haller, and Patterson to analyze Mega. And this work to analyze Mega has led to quite a few interesting results. It's led to 3 different papers, and each of these papers have their own set of contributions. But for this particular work, it led us to defining the HNP sum problem, and it allowed us to come up with a way to solve it that involves some unusual lattice techniques where we're looking for dense sublattices. Another interesting thing that came up with this problem is that we discovered there's this surprising application to the implicit factoring problem, which has nothing to do with Mega, and we wouldn't have been looking at otherwise. So the fact that Mega was cryptanalyzed in the first place allowed all of these developments to happen. And even though we were surprised by the application to implicit factoring. We're hopeful that there are many more applications for H&P sum in the future, and we look forward to seeing what they are. So with that, thank you for your attention.
Okay, thank you, Keegan. Do we have one very quick question?
So did Mega tell its customers that now any logins have potentially fail?
I'm not sure. I think they did have a blog post with the 2 logins. For our 6 login, they just updated their blog post. And one of the things about our blog post is, or our attack, is that our attack is defeated by the same patches that came out for the previous attacks. So as long as you had patched for the previous attacks, you're secure against our attacks. But that's not true for the new set of attacks that just came out.
Okay, thank you, Keegan. Let's thank Keegan again.
Yeah, thank you.
Okay. Our next talk is by Leo Duca and Shane Gibbons on hull attacks on the lattice isomorphism problem. And Shane will give the talk.
Can you hear me okay? Yeah. Okay. Yeah, thank you for the introduction. And congrats again to the previous speaker for the best paper award. So I'm Shane. I'll be presenting my joint work with Leo Duca on hull attacks on the lattice isomorphism problem. So I'll actually be presenting one hull attack, which is a geometric attack on the lattice isomorphism problem. There's also a arithmetic attack that I won't present today, but is available in the paper. So lattice isomorphism. Well, intuitively, you can think of it as a rotation of a lattice. Shown here, for example, the lattice on the left, which in reality spreads out infinitely in every direction, rotates and is isomorphic to the lattice on the right. It's very obvious here in 2 dimensions that they're isomorphic, but in higher dimensions, this is non-trivial. So this lattice isomorphism problem comes in different flavors. The distinguishing variant of this problem, called delta LIP, is the challenge to decide which of 2 lattice isomorphism classes that a given lattice falls into. The search variant of the lattice isomorphism problem is, as you would expect, finding the isomorphism if you know it, if you know there is one. And delta lip has been proposed for use in cryptography by Bennett et al. At Eurocrypt of this year, and by Ducav and Vorden at Eurocrypt of last year. And the signature scheme Hawk presented at AsiaCrypt of last year by Ducav et al. They use search lip for their hardness assumption. So formally, 2 lattices, L and L prime, they're said to be isomorphic if there exists some orthonormal transformation O, sending one lattice to the other. O times L is L prime. Computationally, of course, we don't work in terms of lattices, but instead in terms of bases. So here, you're tasked not only with finding the isomorphism, this matrix O, but also you have to deal with the fact that a lattice can have infinitely many bases, and therefore you also need to find the change of basis U, this invertible matrix U. Yeah, and so if you want to use lattice isomorphism for cryptography, then you of course need some idea of the hardness of these problems. So all known attacks against lip, specifically delta lip, require solving the shortest vector problem, SVP. And the running time for this heuristically depends on the length of the shortest vector, really the relative length of the shortest vector. And so what this means is if you have an exceptionally short vector in your lattice, then you expect it to be easier to find this short vector. And well, what does exceptionally short mean? It's short relative to what you would expect the length of a short vector to be in a lattice of a given dimension. And this value is known as the Gaussian heuristic, given there on the right, or rather its approximation is given on the right. And for a random lattice of dimension n, you would expect lambda1, which is length of the shortest vector, to be around this, this length. And to quantify the difference in the true shortest length and the expected shortest length, we use this ratio called the gap. And the gap is, well, exactly this. It's the ratio of the Gaussian heuristic with the length of the shortest vector. Since any lattice isomorphism style problem can be solved both in the primal and the dual, you need to take into account both the gap of the primal and the dual lattices. And well, to make concrete what I said earlier, having a lattice with an exceptionally short vector or a large gap means you can use BKZ reduction, which is used to solve SVP. You can use a smaller block size. So the smaller parameter beta, and this will be the key parameter all throughout the talk that we're trying to minimize. You can use a smaller parameter and therefore reduce the running time, which is 2 to the 0.292 beta plus a little o of beta. And just some concrete examples. So in a random lattice, as before, you would expect the gap to be big O of 1, because by definition, you expect the length of the shortest vector to be near to the Gaussian heuristic. And with this, you use BKZ with parameter beta equal n, so full block size. Whereas for a nicer lattice, like the lattice of all integer vectors, Zn, the gap of this is actually square root of n. And with this, you can solve SVP using the parameter beta is n over 2. And from the previous slide, you know that's a quadratic speedup. You're halving the exponent. And in general, if you have a gap of size big O n to the delta, then you expect to use this smaller block size here. So in general, the larger the gap is, the easier your instance, at least heuristically. And so Ducav and Worden give this conjecture to try and encapsulate all of this, these heuristics into one statement. And what they say is that the best attack against delta lip, which they're proposing for use in cryptography, requires solving F approximate SVP in both lattices, where F is the gap of both lattices, actually. And so what this is saying is that to solve SVP, you would use BKZ with a block size, with the block size that you would expect to have to use to solve F approximate SVP, not regular SVP. And so our attack is we extract a sublattice of the entire lattice, which we know has a nicer gap, and therefore we can solve lattice isomorphism a bit easier. And then we reconstruct the entire isomorphism from this isomorphism of the sublattices. So the plan of attack for today is I'll explain what the hull of a lattice is. I'll explain what a construction A lattice is, and this is the family of lattices on which this attack works, or at least it's the one that we show that it works on. And then finally, I'll talk about how you can use the hull to solve lip via an instance of zlip and the code equivalence problem. So the hull of a lattice is defined, is inspired by the idea of the hull of a code. And if you're familiar with coding theory and the hull of a code, you'll know that the hull plays an important part in code equivalence problems. And code equivalence can be seen as the code version of the lattice isomorphism problem. So the hull of a code is given as the intersection of the code with its own dual. And as an example, in permutation code equivalence, the hardness of this problem is exponential in the dimension of the hull. So if you have a code with a trivial hull, then permutation code equivalence can be solved efficiently. So knowing this, it's natural to want to define the idea of the hull of a lattice. However, if you begin with an integer or integral lattice, if you take its intersection with its own dual, then you end up with the same lattice again. So you don't learn anything by taking the hull, and it's useless. However, what we can do is we define the hull using a scalar, non-zero scalar S, and define this hull to be the intersection of the lattice with this scaling of its dual. And we're allowed to do this because this doesn't affect the property of the hull that these code equivalence notions use, which is that the hull of some permutation of your code is the permutation of the hull of your code. And the same in lattices, the hull of using this definition, the hull of a rotation or isomorphism of your lattice is equal to the isomorphism of the hull of your lattice. And so construction A lattices are the lattices where this is most obviously useful. And so these are lattices generated by codes. And so your linear code over FP, you can kind of include it into the integers using abusive notation. Here, just write your code as a set of integers. And you can imagine it as just in this example here, the code is included in the box of side length 13 here with integer values. And then the lattice generated by this is simply a matter of repeating this box in every direction infinitely many times. And this lattice has a nice basis and everything that we can work with. Importantly, the lattice hull of your construction A lattice coming from the code C is equal to the construction A lattice coming from the hull of your code. And as before, codes with a trivial hull are easier to work with. And it's the same here in construction A lattices. So if the code which generates your construction A lattice, if this has a trivial hull, then as you can see from the right-hand side here, the hull of this lattice is going to be these red dots here, essentially the corners of the box from the previous analogy. And as you know from a few slides previously, solving SVP on a lattice that is a scaling of z to the power n is much easier, is much faster, because you can use the parameter beta equals n over 2. And this is a quadratic speedup again. So the instance of isomorphism that we'll solve is given construction A lattice from a code, and given two rotations of this, O1 and O2, we have two different lattices, L1 and L2, given here on the top left and top right, and we know they are isomorphic to C plus P times Z to the N, even though we don't need to know what C is here. And what we do is we take the hull of each of the 4 parts of the diagram here, and we know now that the hull of L1 is isomorphic to P times Z to the N, and similarly for L2. But if we now solve our instance of Z-lip, that's to say we solve the instance of lattice isomorphism from the hull of L1 back to P times Z to the N, we don't necessarily get the entire isomorphism, because what we've done is we found some isomorphism from L1 back to some other code, C1 plus P times Z to the N. And the same for L2. We found some isomorphism that sends L2 back to C2 plus P times Z to the N for some code C1 and C2. And so we need to find what element of the automorphism group of P times Z to the N applies here, which would send C1 to C2. And if you're familiar with code equivalence problems, that's exactly what this is. So after we apply the isomorphism that we have found to L1 and L2, and we reduce modulo P, suddenly we have C1 and C2 are equivalent via some element of the automorphism group of P times Z to the N. And such an element is always a signed permutation. That's to say, a permutation of the coordinates and a possible flipping of the sign of the coordinates in your code. What we show in the paper what we show in the paper is that this instance of signed permutation can be reduced to an easy instance of permutation equivalence. And this differs to, so this is using a technique of Sandrier and Simos on a paper of 2013 called The Closure. And their instances reduced to hard instances of permutation equivalence, whereas R1 we show reduces to an easier instance. And so in summary, how the attack works is, given some linear code with a trivial hull, our instance of lattice isomorphism is 2 rotations of the construction A lattice coming from this code. And we know that the hull of L1 and L2 are both isomorphic to P times Z to the N. So we solve the instance of isomorphism from these hulls back to P times Z to the N, and we've solved the entire isomorphism up to some element of the automorphism group of the hull. This element of the automorphism group can be found by code equivalence, by just reducing the rotation modulo P, the 2 rotations modulo P, and solving this easy instance of code equivalence. And so finally, the result is that we must update the conjecture given by Ducave and Worden, essentially to take into account all of the possible hulls of the lattice. And in fact, we show that there are only, you can see on the bottom, we define the hull gap to be the maximum over all integers S dividing the determinant of B transpose times B. We show that there are essentially every possible hull where S is some non-zero real number. Every possible hull is simply a scaling of some hull for an S in a finite set, and that finite set is the integers dividing this determinant. And so finally, the recommendation resulting from this would be that if you have an instance of lattice isomorphism, either search variant or delta lip variant, then then you really should instantiate this with lattices that, for example, have only unimodular lattices which have determinant of B transpose B equal to 1, and therefore the only possible hull that is of interest is the hull when the scalar S is equal to 1, and this is exactly well, the one hull of any integer lattice is indeed the original lattice, and therefore such a lattice is immune to the hull attack. So yeah, that's all I had to say for today. Thank you, and I'm happy to take any questions.
Okay, do we have any questions, Shane?
I'm wondering. Oh, okay, I'm wondering about the arithmetic attack. Is it somehow like related or formed by the same intuition as the geometric attack?
Thank you for asking. So it's really quite different. So it's it's quite perpendicular in the sense that it considers equivalence classes of quadratic forms rather than lattices. So if you have a basis B of your lattice, the relevant quadratic form that you're considering is B transpose B, written there at the bottom. And lattice isomorphism of lattices with bases B and B prime, this is equivalent to quadratic form equivalence for these two B transpose B and B prime transpose B prime. And there's a lot of interesting number theoretic machinery going on in quadratic form equivalence. The problems are the same, but there's it goes into p-adic numbers and the genus and such things like this. So really quite different. And in fact, what we show is that it still is related to the hull in the sense that taking the hull of a lattice and then trying to apply this machinery won't help you anymore as well. So it is in some sense a kind of failed attack, but it is still relevant to know. Thank you.
Okay, thank you, Shane. Okay, the final talk of the attack session is a key recovery attack against Mitaka in the T-probing model. The paper is by Thomas Prest, and the paper will be presented on his behalf by Chris Bykert.
Apologies for interrupting. We're not getting sound in Zoom.
How is it now? Much better.
That's good. Thanks.
So due to leakage in the signing procedure, these early schemes were broken. I'll say more about that. Then in 2008, there was a fix at the design level, allowing for an actual proof of security in the random oracle model due to Gentry, Picard, and Vaikunjanathan. If you then consider side channel leakage, so going beyond the black box model and consider side channels during the signing procedure, these schemes can again be attacked using information gained from the side channel. And then last year, another design level fix was proposed in this work Mitaka from Eurocrypt 22. And in this work, we show that the T-probing leakage model, which was the one considered by the Mitaka work, actually can be used to attack and break this scheme due to a flaw in the proposed proof that was given for Mitaka. All right, so that's the roadmap for the talk. So first, let me kind of set the stage with these hash and sign signature schemes. So these were the initial attempts at lattice-based signature schemes, which look something like this. So in the key generation, one generates a public matrix A that looks random, that defines a lattice, and then B, which is a relatively short basis of that lattice. And that can be written by A times B equals 0 if these representations are done correctly. And B again has relatively small entries in it, small vectors. So the public key is A and the secret key is B. And then to sign a message, one first hashes the message into some point in space, call it C here. And then we can, I'm sorry, don't call it C. We'll choose an arbitrary solution of A times C equals the point in space. And then C, though in general will be very large, will be a very long vector. And so we correct it by subtracting a lattice vector, an appropriate lattice vector V, which has the form B times some integer coefficients, which are given by B inverse C. And then the difference between C and V is the actual signature. So it looks something like this. This C is an initial solution, and then V is a nearby lattice vector, and the difference vector is the signature. Right. So to check the signature, it's easy to verify. One just checks that S is indeed short, and that A times S equals the hashed message. And this holds because A times V equals 0 by definition. Okay, so that was the original proposal. It's easy to see that this would be correct. And it seems like finding a forgery would involve having to find a short pre-image of this randomly hashed message. And in fact, that's true if you ignore the fact that signatures are being given out. So it's hard to break if you don't give the attacker any signatures, but if you start to give out signatures, which is the usual usage of signature schemes, then it's easy to break. And so this was shown in the so-called parallelepiped attack by Nguyen and Regev in 2006. So the problem is that the distribution of the signature is closely correlated to the shape or the geometry of the basis. So the signature, remember, looks like C minus some multiple of B, right? B times this integer vector. And so it's always in this parallelepiped of B times plus minus a half to the n, right? So it's always inside this parallelepiped centered at C. The nearby lattice vector is the unique lattice vector inside this parallelepiped. So the signatures are actually distributed as random points inside the parallelepiped spanned by the secret basis. And given many signatures, not that many actually, but given enough signatures, the entire basis can be reconstructed using what's called independent component analysis. Right, so it completely recovers the secret key from these early attempts. So the design level solution that followed a few years later from GPV is to introduce some randomization into the generation of the signature. So instead of just doing rounding off B inverse times C, rounding it off to the nearest integers, we instead imagine rounding off to some nearby integers chosen at random from an appropriate distribution. So a first attempt would be to use in each coordinate, we just round off like using a Gaussian, we round off to a nearby integer with some standard deviation sigma 1. And so then the distribution of the signature would look something like this. It would look like not a parallelepiped, but it would be drawn from a Gaussian, like an elliptical Gaussian that has this kind of shape to it, where this shape is still basically the shape of the basis. So it's not a complete solution. It still reveals sort of the geometry of the basis, not everything about it, but the shape of it. And then there's one more trick, which is to say we can kind of account or cancel out the shape of this ellipse by introducing some initial rounding of a corresponding shape, right? And so by starting with rounding off 0 or choosing some random short coefficient vector here, a coordinate vector here, and multiplying it by an appropriate matrix, and then doing everything else, we end up with a final distribution that's completely spherical and isotropic. Right? So the signature in this case would have no leakage, or the shape of the signature has no correlation to the underlying basis. All right, so what you can show formally is that if you choose the parameters in just the right way so that everything cancels out appropriately, this procedure that you get on the right, the distribution you get, is statistically close to a perfect Gaussian. And this allows an actual security proof to go through in the random oracle model, where there's sort of two worlds. The real world is that we hash, and then we use B to sample a short preimage, according to this. But in this ideal world, we can actually imagine choosing a short vector S to start with, and then programming the random oracle to be A times S. Okay. And so this is what enables the proof to go through. Okay, so there are now many different concrete proposals in the GPV family, depending on what kind of lattices you use, how you generate the short basis, what kind of precise sampling algorithm you use in signing. And so there's been several works. Falcon, for example, which was selected by NIST, is one. Mitaka as a follow-up, and there have been many others. There's a different family of trapdoors that can be used that give different kinds of properties. So good. So that's all in terms of the black box model, where the leakage that you get from the signer is just the signatures that are produced from this black box. But now let's move into side channel attacks. So side channel attacks say, well, in reality, signers aren't black boxes. They're doing computation, and they may be leaking information about their secret operations. We saw many examples this morning. So examples would be like how much power the signer uses, what electromagnetic emissions that it puts out, timing that the various operations take, even acoustic emanations from processors can be used as side channels. And so when people have taken a look at these signing procedures, they've looked at, okay, well, is there side channel information we can use to then mount parallelepiped style attacks by getting partial information during the signing procedure, right? So in Falcon, remember that a signature looks like this initial solution C minus this lattice vector that's near C. All right, and this lattice vector is some integer combination of the secret basis. Right, and so if you monitor power consumption or other side channels, you can get information about these coefficients Zi here. And so there have been a couple of side channel assisted parallelepiped style attacks. From Teaches last year, power analysis allowed you to detect when, for example, the first coefficient Z0 here is a 0 or a 1, and that allows you to know that the signature lies in some kind of band, or that rather the vector V lies in some kind of band, and that gives you information about B0. And then a second work at Eurocrypt a week or two ago showed that you can even get enough information if the Z0, so one of these coefficients, whether it's positive or negative. So it tells you which side of this half space it lies on, and that's enough information to mount a parallelepiped attack as well. So the most robust countermeasure that we have against side channel attacks is masking, which is widely used. And the idea of masking is to split each sensitive value in the computation into a bunch of shares, so basically secret share them, so that the real value is just the sum of all these shares. And you can then analyze algorithms in this so-called T-probing model, where you allow the adversary to see up to T sensitive values in the computation, but no more. Right? So this is some kind of interesting model for side channel attacks. It's not the complete most realistic model, but it allows us to say something. It's a good starting point for understanding things. So if you split values into D shares so that all the shares are random, subject to the constraint that they add up to the actual secret value, then you can get T-probing security using MPC style techniques. And so if your operations are linear, then they kind of interact nicely with this linear sharing, and everything can be done quite efficiently. You just have linear overhead in the number of shares. If your operations are multiplications, then you have to do some more interesting MPC style multiplications, and there's a quadratic overhead, which is hopefully not too bad if you can afford it. But if you're doing more complex operations, then there would be more than quadratic overhead. Good. So in the T-probing model, ideally, you would have no leakage whatsoever as long as the number of shares exceeds the number of probed values. Okay, so this brings us to Mitaka from last year. So Mitaka, one of the features, there's many nice features of Mitaka, but one of the key features that the designers were aiming for was easy maskability. So the algorithms for Mitaka were designed to be easily maskable. And they gave an outline of a proof of this security in the T-probing model. So we won't give exactly the algorithm, signing procedure algorithm, but what I showed you before is roughly how it works. So again, one sort of chooses a random small vector here, multiplies it by an appropriate linear transformation, and then adds C, applies B inverse, and then rounds this off here. So let's look at the different pieces of the signing procedure in the masked setting. So the first point is nice. This initial short random vector can be done offline. So there's not really anything you have to mask. If you can do this offline and store the result, that's fine. These multiplications, so M and B inverse are secret elements, they're secret matrices. And so they have to be masked when you multiply. But these are relatively easy to do because, as I mentioned before, multiplications of two masked values just involves quadratic overhead, just doing a simple MPC technique. So these aren't too bad to do. But the final step, which is the final rounding. So we get this real valued coefficient vector, and then we need to do randomized rounding of each entry. And so how do we mask that? That's the sort of hard part about masking this. So in Mitaka, they proposed a masked Gaussian sampling procedure where you have this C, which is something that you'd like to do randomized rounding on. And C is just shared. So it's masked and it's shared into D shares. And then they want to produce a sharing of the corresponding randomized rounded output. Okay, so the basic idea is just to do it entry share by share. Okay, so you just take CI or CJ rather. So the jth share of C, you do some Gaussian rounding on it, and that gives you a share of the integer. And then the point is that the resulting ZJs are a sharing of the actual Gaussian Z output. Right? And the reason this works is that the sum of D Gaussians is just the square root of D times wider than the initial Gaussian. So this seems really nice. It's a very clean way of doing it. And unfortunately, there is an attack against this, contrary to what was believed. So there was a proof outline given in Mitaka, which says that, well, if you look at the shares of the C value, the input to the Gaussian sampling procedure, any T looking at any T of these, they all look uniform because it's a random sharing of the actual value. And if you look at the output, any T of these looks random, and so we leak nothing, right? But the nature of the attack is that there's correlations between these CJs and ZJs. And so in particular, by design, by definition, the difference between CJ and ZJ is itself a Gaussian distributed. And so if you add up these differences, they're correlated to the overall output of C minus C. Okay. So let's just kind of give a basic idea of the attack. This V is sort of the output of, or rather the secret offset of the trapdoor sampler. And we're going to probe T over 2 of these C shares and T over 2 of these Z shares. We'll just add up their differences, right? Call that W. And this W is one component. It's not the entire component, but it's a small value that's an additive component of the actual signature. And so it tends to be positively correlated with the signature. Right? In particular, W times B0 in inner product with the signature tends to be positive. Okay? And so it's biased in the same direction as the first lattice vector, the first basis vector. So we have the return of the parallelepiped attack. We can get an estimator for B0 by just taking a lot of traces or a lot of T probing traces here. And what's interesting is this is an unbiased estimator of B0 with some noise in it. But as you get more and more traces, the width of the noise decreases as the square root of the number of traces. And so the more traces you have, the easier it gets, the more precision you get for your estimate of B0. So if you get about 2 million traces, you can recover B0 just by rounding off, maybe simple guessing. If you have fewer than that, you can use lattice reduction to find still B0. And even if you have a number of traces which is linear in the number of shares, you can still recover B0 even with a constant number of probes. Right? So this is an asymptotic result, but it happens to be true. So here's a summary of the specific values that one can get. As the number of traces increases, okay, and the ratio of how many traces, how many probes you take relative to the number of shares, as this ratio increases, the work you have to do decreases quite a bit. And this dotted line means that it's a trivial recovery. And these lines above indicate how hard it is to use lattice reduction to recover the basis vector. Okay, so that is the summary of everything. And here's a bibliography of the works. And I'm happy to take your questions.
Well, thank you, Chris. Do we have any questions? No? Well, thanks, Chris, for standing in on behalf of Thomas, and thanks to all the speakers in the attack session. I'll now pass over